Hi everyone, my name is Dr. Adelle Goodwin. I'm a postdoctoral researcher at Curtin, which is a university in Perth in Australia, so I've come a long way. I would also just before I begin, I would like to acknowledge some of my collaborators. This is very much a collaborative work. Kate is one of my amazing collaborators, as well as many of you in this room, so it's really nice to see all of your faces in person for the first time. Today I'm going to talk about some of the radio observations that we have been taking of tidal disruption events, with a particular focus on the kind of prompt radio emission is what I'm calling it. We all know what a tidal disruption event is. We've just had a lovely overview as well, so I'm not going to talk about that too much, but I do love this infographic. It is really great to use in talks. But what I would like to point out that is in 1988, Rees said, when a star passes close enough to be disrupted in a single flyby, almost half the debris escapes on hyperbolic orbits. So if we think about half of the debris of the star escaping, that means that we have a lot of mass that is ejected when a tidal disruption event occurs. And of course, that ejected material is what produces the radio emission. Now, that ejected material can take the form of jets. We have a few handful of events that have shown on-axis relativistic jets. But we can also have other types of outflows. So we see many events where we have radio emission that isn't consistent with a relativistic jet, but it might be more consistent with some kind of lower velocity jet, mildly collimated outflow, or even a quasi-spherical outflow. And so there are plenty of explanations for these types of outflows and what might be driving the radio emission that we see. But at the end of the day, we're seeing ejected material at relatively high speeds, interacting with the circumnuclear medium of the galaxy, so the gas and everything that's in the center of the galaxy. The electrons in the outflow get shocked as they're interacting with that gas, start accelerating around magnetic field lines, producing synchrotron emission. Synchrotron emission, the electrons are accelerated into a power law distribution, and the peak in the cases of tidal disruption events is usually associated with synchrotron self-absorption. So that is what is driving the radio emission. So we can observe that, but it is very difficult to tell the geometry of the emitting region just based on radio observations alone. So in the radio, we see these peaked synchrotron spectra that evolve over time, and the peak shifts to lower frequencies as the emitting region grows. They're visible for years. So the thing about radio emission from TDEs is it's much longer time scale than optical and X-ray emission. So I've been tracking an event for about 5 years now, and it is still evolving in the radio. So it's kind of a much slower time scale. And when I'm talking about prompt emission, I'm therefore talking about emission in the first couple of years, which might not be your definition of prompt. So again, just to kind of refresh, we have these two types of TDEs that look very different in the radio. So we have a few, like AT2022 CMC, that produce an on-axis relativistic jet. Now, these are extremely luminous in the radio, energies of about 10 to the 52 ergs, but they're very rare. So only 1 to 2% of events show these on-axis relativistic jets. And then we have the non-relativistic events where the radio emission could be maybe a jet, it could be a mildly collimated outflow, or it could be some kind of quasi-spherical outflow. And these are much less energetic, they're about 10 to the 49 ergs, but they're much more common. So we've been finding that about half of TDEs produce these non-relativistic outflows, or at least detectable non-relativistic outflows. So there are plenty of open questions, such as what type or types of outflows produce the radio emission in TDEs, and what drives the differences in the radio emission from TDEs, because they definitely don't look all the same. In fact, I don't know any that look similar in the radio, as we're discovering. So this is a light curve of radio luminosity. So we have time on the x-axis, luminosity on the y-axis. And this is how many radio-detected TDEs we had about 5 years ago. So not very many. We had Swift A1644, which was this really luminous one up the top. That was an on-axis relativistic jet. And then we had a handful of lower luminosity, kind of late time, so detected up to 100 days after the initial flare events. I'm happy to say that now we have many more. So this radio detections of TDEs has really exploded in the past 5 years, and this is thanks to dedicated radio follow-up programs. So we're learning a lot about these events in the radio, and there's a lot of more questions perhaps than there were before we had these observations. But yeah, you can see that there's a huge diversity in the light curves. Some of them only ever decay, some of them start to rise and then decay, others rise really slowly and then decay. And then again, others show these late time flares, which is a relatively newly discovered thing. So, you know, we're talking 1,000 days post-initial flare, we're seeing radio emission rising quite rapidly. So it's very interesting. Just to point out again, these are the relativistic events. You can kind of see that they are much orders of magnitude more luminous than the more common non-relativistic TDEs. So what have we learned? Well, we've learned that radio emission is relatively common. So about half of events show detectable radio emission. Now, this doesn't mean that the other events don't produce radio emission. It just means that we might not be able to detect it. There is a lot of diversity in the population, and we have this rising radio emission. Now, I'm not going to go into too much detail on this because this is not the focus of my talk, but I know that there are some fantastic talks later in the conference that will talk about these events. That we have, for example, Assassin 15OI, which is the orange one, and AT 2018 HYZ, which I don't know if it's plotted here actually. Maybe it's the pink one. And so this kind of very late rising radio emission was quite surprising. There's plenty of theories. I'm sure you probably have your own theory about what could explain this, but it could be that it was an off-axis relativistic jet that has kind of laterally spread at late times and come into our view, or it could be a jet that was launched at late times, or new interactions with the interstellar medium. So if you have a clumpy second nuclear medium, the shock can kind of get reshocked as it encounters a denser region of the galaxy. So back to the original question, what drives the differences in light curve evolution? And in order to answer this question, we really need to delve deeper into the radio observations. And so to do that, we've been systematically following up TDEs. Now, I am part of two programs. The first is a VLA large program that ran from 2020 to 2023. Kate was the PI of this program. We triggered on 24 TDEs during that time. They were mainly optically discovered ZTF events, and that was with the VLA. And then I'm also part of a Southern Hemisphere program where we've been following up X-ray TDEs that were discovered by Rosetta. Now, this is a different population to the Rosetta TDE paper that has been published because these sources have not been published yet, but will be this year, hopefully soon. So this was an Rosetta collaboration that we had where we were looking in the southern sky. So we were following up in the radio with the Australia Telescope Compact Array, which is a radio telescope that we have down in Australia. And so far, we've observed a sample of 26 TDE candidates. I say candidates because it is quite difficult to tell sometimes, especially if you only have X-ray observations, with ATCA. So I'm going to now talk about some of the TDEs that we have discovered and what we have learned. This is my favorite TDE. I don't know if you'll have a favorite TDE, but this one's mine. AT 2019 AZH. Now, this one is really interesting because we detected the radio outflow just 10 days pre-optical peak. So very early radio emission. Probably, I think it's the earliest radio emission that we have discovered. So this is the light curve at 9 gigahertz. I published up to the last 4 points. So here are some more points for you to have a look at. But this TDE is very interesting because it showed a really slow rise. So it took about 300 days to rise to peak. And now it's showing an even slower decay. But it is quite bumpy as well. So there are some things that look like little flares with the general trend of the light curve. This one, we just saw that it had that late time X-ray brightening. So I've pointed out where that was in terms of the radio light curve to see if there's any correlation between the X-ray and radio, which would maybe indicate that some of the radio is produced by an accretion-driven outflow. And then maybe was some kind of bump in the light curve that occurred after the X-ray brightening. But it is hard to say. But now it actually seems to be decaying as well, perhaps a set of Taylor decay, which is quite interesting. And in fact, if you run through the calculations, the peak of this light curve, 300 days, it seems quite late. But if you look at the kind of expected deceleration time of a ballistically expanding outflow that is sweeping up material from the second nuclear medium, it can actually just be a single ejection of stuff into the outflow that is then slowing down after it gets to the peak. So very interesting source, this one. But not only do we have light curves, we also have radio spectra. So at each epoch, we have a radio spectrum from about 1, maybe slightly lower, to 15 gigahertz. And so this then enables us to model the radio emission. If we have synchrotron spectra, we can model, hopefully, the peak, if our radio spectrum covers the peak. And then we can get an estimate of the size of the emitting region. We can also get an estimate of the energy in the outflow at that point in time. And if we track this over time, we can then watch the outflow grow, and we can estimate the velocity of the outflow. And this is then key to maybe what produced the outflow. And so we do this. I do just want to point out that this one is quite strange because at late times we saw the optically thin spectral index change and fluctuate. So that's the P of the synchrotron emission, if you know a lot about synchrotron emission. And we don't think this is associated with cooling of the electron population because the timescales just don't quite work out. The cooling would occur on a much longer timescale. So our best theory was that perhaps it is an inhomogeneous circumnuclear medium. So it's quite clumpy. Maybe the population of electrons are kind of getting slightly reshocked and you're getting a slightly steeper synchrotron spectral index over time. But if you've got a theory, let me know. So yeah, as I said, we can model the synchrotron spectra. We can then model the physical properties of the outflow. So we can get the radius, the energy, the velocity, even the density of the circumnuclear medium with very large error bars, and the magnetic field strength. And so if we do this, we can see that the velocity of this outflow, depending on the geometry that you assume, so again, we know nothing about the geometry, we have to assume that in our modelling, which is quite a downfall. It's anywhere from about 10 to 30% C. So definitely not a relativistic event, and even if we had an extremely narrow jet, this event would still not be consistent with a relativistic jet. So it's definitely a non-relativistic outflow, but what type of outflow and what it was launched by is the question. And the other really key thing is that if we track the radius over time, we can track it back to time equals 0. And we found that in this event, the radius, the outflow was launched coincident with the initial optical flare. So not even the peak, when the first optical flare was observed, the outflow was launched around that time. So this is what I call a promptly launched outflow. And so we don't want to just do that for one event. It would be great if we could do it for all of them, or as many as we can. And so we've been taking radio observations, looking at the spectra, modeling the spectra, estimating the radius, the velocity, and all those sorts of things for as many events as possible. I'm just going to highlight AT 2020 OPY and VWL, we observed both of these with the VLA, but also J2344. So this is the best eRosetta TDE candidate in the southern sky. And we also observed a radio outflow from it, which is pretty cool. And so we can then model the physical outflow properties of all of these events. And we keep going. We can then track the radius back, figure out when the outflow was launched likely. And if we do this for a population, we end up with a plot that looks like this. So this is time on the x-axis and radius on the y-axis for a number of different TDEs where we've been able to do this modeling. And for all of these events, if you track the radius back with time, it was launched coincident with the initial optical flare, or X-ray flare if there was no optical flare. And so all of these events produce very prompt outflows. And so that then begs the question, what is launching these outflows at very early times? And then I just want to highlight some of the eRosetta TDEs that we have discovered. So as I said, 2344 was the best candidate that we have. It actually also had an optical flare that was observed in Gaia, but we discovered it in the X-rays with eRosetta. And it also had a WISE infrared flare, which is very interesting. So we have looked at a sample of 26 soft X-ray transients from eRosetta that were selected to be good TDE candidates. And so far we have reduced 11 of the ACRA observations, and we've detected 7. So again, we're looking at about half of the population of X-ray selected TDEs are producing radio emission, which is similar to what we see in the optical samples, which is interesting. So these are some of the light curves that we're getting. On the top is the X-ray, then we have infrared, then we have radio, and then we have optical. So the interesting thing about some of these candidates is that there was no optical flare detected, but there was in some of them an X-ray and/or infrared and radio flare. So this is just kind of a brief look into the sample of the X-ray selected TDEs and the radio outflows that they are launching. And what we're finding in most of these radio outflows that we've seen is that these also look like prompt low velocity outflows. So we're able to track the radius back, not as well as we are when we have higher cadence observations, but they look like they are they are launched approximately coincident with the initial X-ray flare or optical flare. So, to kind of summarize, more than 10 TDEs show radio outflows that are launched coincident with the initial optical or X-ray flare. These outflows have energies of about 10 to the 47 to 10 to the 50 erg or so in the radio, and they have velocities of 5 to 30% c, depending on the geometry that you assume. So what types of outflows could explain these? And so could these be a jet? They're definitely not a relativistic jet because they're not luminous enough or fast enough. But maybe it could be some kind of sub-relativistic jet from accretion, a more mildly collimated jet. Again, maybe that's a jet, maybe that's just an outflow. I guess it depends on your definition of jet. Or an accretion-induced wind. So, we know that we have accretion occurring. We know that accretion is quite an inefficient process. This could blow off some material and we get some kind of spherical outflow launched during the accretion process. But these two types of outflows, perhaps, not necessarily, but perhaps require some kind of correlation with the X-ray emission. And not all of these events show X-ray emission, but again, maybe it's just not detectable because it's lower luminosity. But these are kind of black hole accretion driven, and so we should see some maybe kind of correlation between a jet or an accretion-induced wind and X-rays, which trace the accretion, perhaps. Alternatively, we could launch a very early outflow with like this kind of collision-induced outflow scenario where as the debris is circularizing, it collides with itself, and this then drives and outflows and ejects material. This would be kind of also quasi-spherical, and this doesn't have a dependence on the accretion flow necessarily because it is launched as that debris is circularizing before accretion onto the black hole. Alternatively, again, we have this unbound debris stream. This would be launched very early. We would be seeing the fastest unbound debris, but this debris stream would probably have quite a narrow viewing angle, and so perhaps we wouldn't necessarily be seeing that. But these two types of outflows are kind of these debris-driven outflows, and they would be launched very early on in the disruption process. And then on top of that, not only do we have the mechanism of the outflow that affects the observations, but we also have the environment. And so the circumnuclear environment of the host galaxy affects the radio emission that we see because of how powerful the shock is. If it's quite a dense circumnuclear medium, you can drive quite a powerful shock. You can have a more energetic radio emission that we see. And so all of these things come together and we kind of try and disentangle what type of outflows that we're seeing, and then what we can learn about the disruption process, the black hole accretion, how much is ejected, as well as the host galaxy from the radio emission. So it's very complicated. My favorite theory is the collision-induced outflow for these prompt outflows. For the late time flares, I think it's a whole another can of worms. But yeah, happy to discuss this and hear your opinions on what is driving these radio outflows. And I think that's the end, so I'll leave my summary slides here. Thank you.
All right, let's thank Adelle for that very interesting talk. And I see Eric is already heading to the microphone.
Did you look at any correlations with the black hole mass for any of these, like correlations with the energetics of the radio?
Yeah, well, so not yet. We are looking into things like that at the moment, but at the moment, most of these radio observations have just been presented as standalone single source papers. We haven't really made an entire sample paper yet, but that is something that we are doing in these different collaborations. So that, yeah, is something that we will look at soon, but we don't quite have those results yet.
Okay,
there was an interesting paper by Taraneh Takari about the jetted TDEs that was just on arXiv this past week that suggested maybe the ones that have the on-axis powerful relativistic jets may have lower black hole masses. But I think that's the only published work I'm I'm aware of on that, as Adelle said. All right, looks like we have lots of questions. So I'm going to alternate across the room. So Vikram, go ahead.
Yeah, really cool observations, Adelle. What are your thoughts on continuous energy injection versus a sort of single explosion that's empowering some forward shock?
Yeah, so I think it's a good question. For most of the promptly launched outflows that I have shown, the rise in the light curve can actually be powered by the outflow sweeping up material from the circumnuclear medium. You don't necessarily need continuous energy injection. But that doesn't mean that that's not happening.
Okay.
So it is actually quite difficult to discern
Yeah.
with the radio observations alone. So you really need to look at the other wavelengths to see if there's any indication of continuous injection into the outflow.
All right, we're going to alternate back across the room.
So could you give us a sense of what sort of the temporal uncertainty of associating the prompt radio with the optical X-ray? I couldn't really tell from the plots. Is it a month? Is it a few weeks?
So you mean like when the radio flare occurs?
Yeah, exactly.
Yeah,
When
I
it's
mean
not so much the timing of the radio flow, the timing of the launching of the outflows, which you were associating.
Oh, so for all of the events that I've looked at, the radio outflow is like launched within like 10 to 20 days of the initial flare. So it's very like, yeah, because often the peak is only, 30 to 50 days from the initial launch. And so, yeah, but often it's actually quite narrow. Because I mean, with the synchrotron emission, you can get quite good constraints on the emitting region size. And so we can, yeah.
Thank you.
Back over here.
Hi. I know maybe it's early days, but what do you think about homogeneous radio selection? I think you're doing that. And if you can trace back with your SED study when the TD might have happened, and you'll find that a lot don't have either optical or X-rays, maybe some have infrared, the obscured ones. Do you know we can sort of find overlooked TDs in most wavelengths with radio? Or?
So, I mean, yeah, I think there are people that have been looking at radio surveys trying to find TDEs, but it is really hard because at radio there are a lot of AGN that do really weird things. And so distinguishing between a TDE and an AGN flare in the radio alone is very difficult. So I think it's worth doing, but there is that caveat that anything in the radio that is a flare could just be an AGN flaring. And you really have to look for the multi-wavelength properties to try and figure out if, is it soft enough to not be an AGN? Is there an optical flare? Is there other things going on?
You can trust the WISE data to some extent if they look like galaxies or
yeah, of
AGN.
course. Yeah. But yeah, even that has some uncertainty.
Sure.
All right, Brian?
Thanks for the nice talk. In the early days of this field, I had a good-hearted disagreement with Short about the origin of the radio emission, where I thought it was something external, like it seems like everyone's modeling it as some kind of external shock, and he thought it was some kind of internal jet emission like you see in steady AGN. And of course, the difference, in an external situation, you shouldn't get huge fluctuations in flux on a short time scale because of, different light travel time effects and things. But maybe that's actually not as relevant in the non-relativistic case. But I guess I'm wondering is can we really disentangle? I mean, do you see sort of flat spectra that look more like sort of steady AGN jets in any phases? And do you have any thoughts on how we would disentangle an external shock from some kind of growing internal, like Blanford conical type jet?
I mean, yeah, in my opinion, it's quite difficult. And I mean, even distinguishing between something that is in pre-existing AGN.
Well, not pre-existing, but just that there's an external shock where the matter from the jet is hitting the external medium, but then the jet, maybe inside the jet itself, if it's a big enough jet, you could get internal emission. I mean,
sure, and that can also drive synchrotron emission. Yeah.
So I think that's a question I think in the internal case, because the emission is at small radii, you can get more rapid fluctuations. I think in the flux. But anyways, I think it's something worth thinking about in the modeling of these. Is at what point do they become more like AGN? But anyways.
Yeah, no, I think the geometry really is a key to that, because if our outflows are consistent with a spherical geometry, then it's probably not a jet. But then, yeah, we need to match the simulations and all sorts of other things to figure out if the geometry is collimated or spherical or something like that.
Thanks.
Back over here.
I jumped the queue. Tatsuya was a.
Okay. Tatsuya, go ahead.
So I have a very specific question on 2019 AZH. And your claim is some set of their phase, this outflow going to this. And did you make some estimate of outflow mass? Because, this is some deceleration happens, so the emission is calorimetric, so you can estimate the total rejector mass.
Yeah, so we can estimate that from the synchrotron emission as well. So that's one of the things that we extract.
Oh, okay.
But it's kind of hard to really look into, because you're looking at the mass in the emitting region, and so what that means is not super clear.
Okay, yeah, thank you.
All right, Jean, if you want to come up and switch your computer over, Wenbin, maybe we can get your question super quickly while we do that.
Thank you. Yeah. So I remember in the past, a very long time ago, Short conducted some radio follow-ups of X-ray selected TDEs. That was a long time ago, maybe more than a decade ago. And the success rate was very low. So non-detection, whereas now you followed up the E-Rosetta ones with 50% success rate. So is it just because the E-Rosetta ones are closer, or is it in what sense? What's the difference?
Yeah, we intentionally selected a redshift range of less than 0.1. So perhaps
okay, I see.
that is the case. I'm not familiar with Stuart's sample. But also I would like to point out the radio emission we're seeing is extremely faint.
Maybe Short didn't try hard enough. I see. Thanks.
No worries.
All right, well, let's thank Adelle again, and we're going to have our last talk before the coffee break.